Hello, everybody. We're going to talk about a few different types of concentration tonight or today, whenever you are watching this. And we're going to start with molarity. Molarity is the most common form of concentration that you'll find in chemistry, and that is measured by the moles of the solute, so whatever's dissolved in water. We're going to assume this is for everything we do divided by the liters of solution. So the solution is going to include the solute and the solvent mixed together. So the liters of the solution. And you'll notice that the higher the amount of moles, let's say we have 1 liter of solution, if I have 3 moles in a solution of a solute over 1 liter, that means I have 3 molar concentration. If I would have 10 moles of solute per 1 liter, that means I have 10 molar. So the more that you have dissolved, the higher the concentration, the higher the molarity, which should make sense. We're not always going to have 1 liter, but that would be just an example of how we would use this. So this is in chemistry the most common way to do concentration. I'm going to do a couple practice problems with you real quick. So the first one we're going to try here is looking at calculating the molarity when 145 grams is dissolved. So I'm going to take my equation, molarity, I'm just going to put a large M, that is how molarity is typically written as far as a unit, and that's going to be the moles of the solute divided by liters of solution. And I don't have my moles given to me. I do have my liters of solution. That's 2.75 liters. But if I figure out my moles of NaCl, I'd be able to get my molarity. Sometimes the moles can be straight up given to you, but in this case, they give us the grams. So I'm going to take those grams, 145 grams of NaCl, and convert them to moles. And I'm just going to use one step, dimensional analysis. There's 58.44 grams of NaCl in 1 mole. That's from taking the molar mass of sodium, which is 22.99, plus the molar mass of chlorine, which is 35.45, and getting that molar mass. So that's what my grams are in 1 mole. The amount of moles in this case would be 2.4811, blah, blah, blah. There's more sig figs there that will carry through. So now I can put that number up here. And I really only have 3 sig figs, so I'll put a line under it and put dots there. So when I take 2.48 with all those numbers carried through, divided by 2.75, my calculator, I get 0.902 molar. That is the concentration of that solution. Let's take a look at a problem that's a little different as far as what is given. In this next problem, we have the molarity given to us, but we're trying to figure out how many grams you would need to make something like that. So again, I'll look back to my original formula. My original formula is molarity equals moles of, in this case, KCl, because that's the solute, divided by liters of solution. So I am going to reset up the equation. I have 1.50 molar equals X, or some amount of moles of KCl, divided by 0.750 liters. So that's the amount of solution that I have. I can solve for moles by multiplying both sides by 0.75. And if I do that, I will get 1.125 moles of KCl. Sig fig wise, I only have to that amount, but I'm going to carry through again. So now I'm just kind of doing the last problem we did, but in reverse. Now I'm trying to make this solution. How many grams do I need to measure out to make that happen? So I'm going to start with my moles here and do a dimensional analysis. Moles of KCl. And then for every 1 mole, I need to cancel diagonally. There are 74.55 grams of KCl. That's by just adding up the K and the Cl from the periodic table. And when I do that with my calculator, I'm going to get 83.9 grams of KCl. 3 sig figs, so I have 3 sig figs in my givens. So how would I make something like this? I would put 83.9 grams of KCl into less than 750 milliliters of water, but then I would get the solution up to 750 milliliters. Remember, the 750 milliliters is the KCl, and the water. So I cannot just add 750 milliliters of water to 83.9 grams because the volume will go higher than 0.750 at that point, which is higher than 750 milliliters. It'll go higher than that, so that I won't truly have the correct molarity on the solution if I try to do that. All right, we'll practice more of those in class. Moving on. The next topic we're going to talk about is what if you have a solution that is strong and you add water to it? A strong solution in chemistry is typically called either a concentrated or a stock solution. And these stock solutions, you can dilute them by adding water to them. If you add water to them, you're just increasing the volume of your solution. So this is a common equation used to figure out how much you dilute things, what the concentration goes to, and such. So what happens is I have a certain amount of moles of, remember molarity is moles per liter, and then I multiply it by my V1, which is going to be in liters. So I'm going to get moles here is going to be equal to my moles that I start with is going to be equal to my moles over here too, because I have moles per liter times liters again. So that's going to be equal. We can think of this as our mole 2 situation. So what are we talking about here? Well, when we start with a certain amount of stock solution, let's say I start with 3 molar stock solution, and I have 50 milliliters of it. If I add 50 milliliters of water, I have not added any of my solution at all. Let's just say it's HCl that I'm talking about. I haven't added any solute at all. So my moles of solute are the same at the beginning and the end. My moles have not changed. My liters have changed. My volumes have changed. And we can figure out what has happened to the concentration because of that change. So let's just, for example, we can do this one real quick. 3 molar would be my original concentration, and I had 50 milliliters of it. That's my original volume. And the volumes can be in milliliters or liters, just so each side is the same. They'll cancel out that way. Now that I've added 100 milliliters or 50 milliliters of water, I'm curious what my new concentration is by diluting it and added that much water. My new volume is now 100. I've added water. I don't have 50 milliliters anymore. I now have 100 milliliters total. And it probably makes some sense here that this is just going to cut in half. If I divide this out, I'm going to get 1.5 molar. I know we have sig fig issues, but it's just a quick little practice problem. We'll do a couple other practices here real quick. This is a little bit more of a practical situation of something that I would need to mix often, and that is taking some stock solution of hydrochloric acid and trying to dilute it down to concentrations that we would use in a classroom more often. So I'm going to use M1V1 equals M2V2. So it doesn't matter which side you set which to, so I'll just put what I'm looking for on the left-hand side right now, times V1, which is 3.00 liters, and my stock solution is 12.1 molar. So the question is, how much of that stock solution do I need? If I do the algebra and take 1 times 3 divided by 12.1 and solve for V2, so I'm getting V2 by itself, if I do that, I get 0.248 liters, or 248 milliliters. So if I'm going to make a solution like this, I'm going to get what's called a volumetric flask. It is shaped like this. It looks kind of weird. There's a line on there, and let's just say I had a 3-liter volumetric flask. That line would indicate it's exactly 3 liters when I get water up to that line. So what I would do is I would add 248 milliliters of the HCl, the concentrated HCl, into there, and then I would fill the rest of it with water. I would dilute it to 3 liters. I would dilute that solution by adding the rest of that water. So the rest of it would be, not quite 3 liters, obviously, but like 2.7, yeah, something like that. But we're going to add the rest of it. And you could do the math quick, but we're just going to add the rest of it water, and that's how you would actually make it. And we'll talk more about that in class 2, how we would make that thing with, or make that solution. So in the molarity equations, we talked about how we can make a solution. That'd be if you started with a solid. Now we're talking about making solutions. Really, you're just starting with a more concentrated liquid and how you would make those solutions. So let's try one more like that. Again, we have M1 V1 equals M2 V2. I'm going to pick the left side this time to be the stock. Again, it does not matter which side you pick. And I'll see what my V1 would be in this case. I want 0.50 molar, and I want 250 milliliters of it. If I solve for V1, in this case, I'm going to get 8.62. As you can see, I only have 2 sig figs, so we'll stick with 8.6 milliliters that you would have of the stock solution. So that means, again, if I had a volumetric flask, my great picture of this, if this was a 250 milliliter volumetric flask, which we definitely have, I'd put the 8.6 milliliters of the stock solution in there. And then the rest of it, the 241.4, the rest of it, milliliters, would be water. So it helps us understand when we dilute, when we add water, first of all, what concentrations are things going to, or if there's a certain concentration we need, how would we go about that process? There's 2 more concepts that we're going to talk about here quickly, and that is as far as other types of concentration measurements that would be found in your everyday life and in science in general. Percent concentration is a pretty common thing. If you go to the store, you can see hydrogen peroxide is 3%. There's a lot of different percentages in our everyday life, and this is for concentration also. So the ocean is about 3.5% NaCl by mass. If you had a 200-gram sample of that ocean water, how many grams of sodium chloride would be dissolved? So based on the equation above, the percent concentration, and that's after you've taken the grams of solute divided by grams solution times 100%, but the percent concentration is equal to those. In this case, it's 3.5. I'm going to take that 3.5 and change it to decimal form. So 0.035 is equal to how many grams of NaCl I would have over grams of solution. Well, in this case, my grams of my ocean water is 200 grams. So to get my grams of sodium chloride, I could take 0.035 times 200, and in this case, my X, I just call it X, I guess. In this case, X is equal to 7.0, because I have 2 sig figs, grams of NaCl. So if I had 200 milliliters of that, I would expect, or 200 grams, I'm sorry, I would have 200 grams of ocean water, I would expect to get 7.0 grams of it to be sodium chloride because of that. So that's just one example problem. Again, we'll do more example problems in class. This is just get you an intro to all the different types of concentration and how we can use them. You will get the formulas, just a matter of being able to use them again. One last type is parts per million. Parts per million. A couple different ways of looking at this. It's how many grams there are for every 1 million grams of solution, or it's also how many milligrams of solute there are in a liter of solution. So a couple different ways of looking at it. You have to think about what do you have for information. How can you, as far as trying to solve for ppms. If you are given those 2 things, how could you solve for the ppms? If you're given the ppms, just depends, just like any problem solving, what do you have given to you? And then when you have that given to you, what can you, how can you get to what you need to solve for? So in this case, we're talking about, so an example problem quick. 2015, Sartell water, I just looked up on the Sartell City website, and they had a fluoride ion concentration. They measured different chemicals in the water every year and report it back to their residents. But in 2015, Sartell water has a fluoride ion concentration. That's required by law that they add fluoride, but what was measured to be was 1.11 ppm, or parts per million. So my question is, how many liters of water would I need if I was going to get 1 full gram of fluoride ions. How could I do that? Well, I'm going to set up the equation and look at 1.11 ppm. Whoa, that's too many P's. We'll do this. That's ppm. Is equal to grams of solute. So I'm going to put 1.000 grams of fluoride ions here. We can do that. And that's divided by liters of solution. Again, if I want to solve, let's just say that, call that x. If I want to figure out the amount of what x is, I'm going to have to multiply both sides by x. Let's just do that algebra real quick. Multiply both sides by x. And then if I want to get the x by itself, I'm going to take 1.000 divided by 1.11. And I would need, to get 1 gram of fluoride, I would need 901 liters of water. So it's not a lot of fluoride in all of our water, but there's some. There's that 1.11 is about what they have on, that's the average measurement that was made in 2015. So it's a quick intro to the different types of concentration we'll be working on in class on Thursday. You'll get the equations, but you do need to be able to manipulate them and problem solve based on the information that you are given. Thank you.